Log on, tune in, find out. Another good idea from Cambridge.
In the entropic central limit theorem.
Thank you. I'd like to thank the organizers for the invitation to come here and possibility to talk. It's a joint work with Chistikov and Goetze.
Have you switched the microphone on?
Microphone?
Yeah.
Where is microphone? You mean this one? Where?
No, it's true.
Yeah. One. One. No. So I try to be louder. Gennady Petrovich Chistikov and Friedrich Goetze from Bielefeld. Let me introduce basic notations and setting. Assume we have a sequence of independent, identically distributed random variables, x1 to xn, etc., with mean 0 and variance 1. And form the normalized sums. Standard object, and the central limit theorem indicates that weakly in distribution, the normalized sums are convergent to standard normal law. Or equivalently, in terms of the distribution functions, one may consider the Kolmogorov distance between Fn and phi. Whereby Fn, I denote the distribution function over the n, and capital phi denotes the distribution function of the standard normal law. With density, I will use it later on, little phi. There has been done a lot of research about this statement, in particular about the rates of convergence with respect to the Kolmogorov distance. And the most classical result is Berry-Sen theorem. So let me remind a few results about Kolmogorov distance. It was proved in 40s that in case of the finite third moment, up to some absolute constant capital C, we have the rate 1 over square root of n. It's a typical rate, and it cannot be improved if we require existence of high moments of the underlying distribution. For example, for the Bernoullian random variable xi, it's correct behavior 1 over square root of n. If the moments of order smaller than 3 exists. And this finite, there are similar results, in particular by, for example, Ibragimov. In 60s, who proved that if the moment of order S is finite, where S is strictly between 2 and 3, we have convergence also with some rates, namely let me write O capital of 1 over n raised to the power s minus 2 divided by 2. So it's somehow worse than in the Berry-Sense theorem. And actually the rate can be as low as we wish. It can be arbitrary. It was noticed not long ago, one can say, in a work by Matskevicius. In 93, it was proved that for any prescribed sequence epsilon n, one can indicate the law for the underlying distribution for x1. It could be rather good, symmetric, with bounded density, etc. But the Kolmogorov distance may decay to 0 it will be greater than epsilon n. Such results are generalized to the case of non-identically distributed random variables, a lot of in terms of Lyapunov ratios or coefficients. And another way to sharpen Berry-Sense theorem is to prove this inequality for a stronger metric. Or distances, and most standard choice is the total variation norm. And this is what I'm going to discuss today. It's entropic distance. Or relative entropy. I will write the definition a bit later. But first let me emphasize that in order to obtain a convergence to 0 for the total variation norm, which is weaker than entropic distance, some additional assumptions are needed. Not moment assumptions, because for discrete distributions, of course, the total variation is 2. And also, with respect to total variation, the picture is more or less complete. And first it was proved by Prof in 50s that if x1 has a non-trivial absolutely continuant component distribution, for example, if x1 has density, then we have convergence also in total variation. And the rate of convergence was studied later on by Sirajdinov and Mamatov. Who found exact asymptotic for the total variation. In case of finite third moments. So it is again like in the Berry-Sense theorem, it was a natural assumption, and to get the rate 1 square root of n, and then this distance is equal to approximately 1 over square root of n plus O little of square root of n, where the constant c is proportional to the modulus of the third central moments. Good, it's like some prehistory about convergence, about the rates of convergence. And now let us turn to the second metric, not metric exactly, but distance. First of all, I need to introduce a couple of functionals. Given a random variable x with density p of x, the entropy of x is introduced as the integral of minus the integral of p log p. The integral may or may not exist in general, and but under mild moment assumptions, it always exists. One important property, also absolutely elementary, is that if the second moment is finite, then h of x not only exists, but also is bounded by the entropy of the Gaussian random variable having the same variance as x. I will use the same expectation as x. Although, of course, this functional is translation invariant, so if you add a constant to x, it will not change. Another related functional is Kullback-Leibler distance. If we have two probability distribution, actually in a very abstract setting, on arbitrary, but even on the real line, if you consider a random variables x and y, then the definition is this, where x has density p, capital Y has density q. This integral makes sense once the distribution of x is absolutely continuous with respect to the distribution of y. And then capital D of x, here capital D of x is the relative entropy of x with respect to z, which is this. It's non-negative. In general, may take the value plus infinity, but makes sense always once there is density. And this integral can be recognized as a difference of entropies. So it can be used as a measure of non-Gaussianity. It shows how close the distribution of x to the distribution, normal distribution with the same mean and variance. And if you consider here arbitrary z and take minimum overall normal random variable z, then minimum is attained exactly for z having the expectation as x and variance. And this functional can be related to the total variation. You know, to see that it's indeed a stronger distance. There is Pinsker type inequality. Which gives a lower bound for the entropic distance to normality in terms of total variation. Fx denotes here the distribution of x. And let us emphasize that this functional is a fine invariant. So if we multiply by a constant, add a constant, it will not change. It's an intrinsic property. And now the starting point is theorem due to Baron. In 1996, who proved that if the relative entropy for at least one of the sums is finite, which is equivalent to saying that the entropy is finite for some and not. Then there is convergence of the entropies in relative entropy, or which is the same, the entropy of the n is convergent to the entropy of the Gaussian limit z. So this entropic central limit theorem. And the statement also creates some questions about the type of convergence, about the rate of convergence, similar to the Kolmogorov distance and how fast the relative entropy tends to zero. That's a very interesting question. And so one can also ask about monotonicity, and what is known, let me mention a few results, is as the following. Arstein, Boll, Barth, and Nahor prove that a few statements in two different papers. The first one is that the relative entropy monotonically decreases to zero. A very nice observation. And for example, we could not say, or with respect to the total variation distance, if similar results may hold. It's total variation is a little bit strange. And second theorem is that this I'd like to formulate somewhere. I need some additional place. By the same authors, and there was independently a paper by Baron and Johnson. Who studied the rate of convergence. So d of the n tends to zero, but in view of the Matskevich's results, in general it may decay as slow as we wish. recalling Pinsker's inequality. But typically it should be like O capital of N. And theorem says the following. Assume that the underlying distribution of x1 satisfies Poincare type inequality with some positive constants. Lambda 1 calls spectral gap. For any smooth function u bounded, the variance of u of x1 is bounded up to this constant by the expectation of u prime of x1 squared. So for any smooth function, and then d of the n, it's O capital 1 over n, but there is an estimate which implies 2 over lambda 1 here d of x1 times 1 over n. A nice estimate which involves very large a family of nice distributions which satisfy Poincare type inequality and gives sharp estimates. But this condition, it's not clear how if it's important, perhaps it's important to get a form or shape of the constant in front of 1 over n, but in the problem of rates, this assumption turns out to be irrelevant. And it's possible to study the rates of convergence only using usual moment assumptions. Now I'm ready to formulate a few statements. Let's start with the following statements. So assume that the force moment is finite, and the entropy or relative entropy is finite for some index and not. Concerning this assumption, it's more general. Of course, in practice one may take usually just one and assume that x1 has density with finite entropy, but it may happen that the distribution is purely singular, but its convolution with itself will be absolutely continuous. Such examples exist, and we studied in 50s, 60s. So it's better to keep a more general assumption like in Baron's theorem. Then D admits the following asymptotic. It's linear with respect to 1 over n. And the constant is proportional to the square of the set limits. So just under the fourth moment condition, it's possible to obtain exact rates like 1 over n. And one may ask, what can we say about the rates in case of high moments from one hand, and on the other hand, what may happen if only the third moment exists? And let me cover the moments of order from 2 to 4. Assuming that the S moment is finite. And then one can study both upper bounds and worst lower bounds. If for some index the relative entropy is finite, then the previous assertion can analogue exists, but it's weaker. Here we should like a little of n log n raised to the power s minus 2 divided by 2. It's upper bound. And it turns out that this cannot be improved. So in case when s is equal to 3, we obtain like 1 over square root of n only in case of the third moments. And second, let's fix number 80. Then there exists a sequence of independent, identically distributed random variables, that is the underlying distribution x1, which can be well behaved, such that for sufficiently large n, we have like this upper bound modulo a power logarithm. So it turns out that the fourth moment assumption is important for such conclusion to obtain 1 over n. Otherwise, no hope. The convergence will be at a slower rate. And one can also study rates of convergence when the S moment of order greater than 4 is finite. So as before, it seems that the corresponding S absolute moment is finite, the entropy is finite for some n. Then the relative entropy can be expanded as a polynomial of 1 over n. Up to the integer part of s minus 2 divided by 2, and the error term will be 1 over n log n raised to the power s minus 2 divided by 2, like in theorem 2. So everything is very similar. Here, every coefficient Cj is a polynomial of a certain polynomial of the cumulants gamma 3, gamma 4, etc., gamma 2j plus 1. Gamma r, the cumulants of x1 is defined by I raised to the power minus r, and the rth derivative of the logarithm of the characteristic function of x1 computed at the point 0. It's also some polynomial of the moments of order up to r. For example, this expansion can be used when x1 has a symmetric distribution, when the third central moment is 0, then we obtain that to complement this assertion that if the sixth moment is finite, so that the previous statement is applied when s is equal to 6, and the third moment is 0, more or less typical also, not always, but make. Then d of the n is proportional, it behaves like c, it's c over n squared, c2, using the previous notations, plus O little of n log n squared, where the coefficient c2 is 1 over 48, and the third cumulant squared, which is the same as first moment minus 3 squared. So, and so on. One may continue. When the first moment of the random variable x1 coincide with the first moment of z, standard normal random variable, up to some order r or k, then we'll obtain 1 over n raised to the power k minus 1.
So what's left open?
Not so much, but there are questions. There are a lot of actually open questions about the relative entropy, especially when it's applied to random vectors in some multidimensional case, and there are some interesting connections between D and between properties of the entropy, entropy power functional, and volume relations in convex geometry. For example, using D, one can formulate slicing problem, reverse Brun-Minkowski inequality, etc., etc. For example, the slicing problem can be formulated as a statement that D is the relative entropy of a given random log concave vector x with respect to the Gaussian does not exceed Cn. Very interesting connection. And Bergain's Clartax results implies that we have an additional term proportional to n log n with constant 1/4. Good, but let's return to dimension 1, to entropic central limit theorem. Actually, by the way, I didn't mention, but there are similar expressions also in the multidimensional case, but with fixed dimension, but they're only asymptotic, not quantitative. For the proof, let me consider the simple situation. I will assume that x1 has a bounded density. Otherwise, one should use so-called truncation of density approach. And D is finite in this case, say P of x. And Zn has some bounded density Pn of x, which can be chosen to be continuous for sufficiently large n. And so I write down the definition of Zn. In the work of which I cited before, of two teams, they used representation of this functional as the integral of Fisher information, which is applied to regularized distributions, convolutions of x with Gaussians. And then they studied the behavior on the basis of this de Bruijn identity. There is another possible approach to deal with this functional. Write down the definition. And try to use theorem about normal approximation of Pn by phi. Variety of so-called local limit theorems, uniform, non-uniform local limit theorems, which say roughly that Pn of x approximate is close to phi of x. And if we do this formally, then we obtain the desired expressions like this. And by the way, physicists in some papers used freely such without any justification. They write even without not saying about the sum of independent random variables. It's saying that d is this functional of x is approximately this. So such formula are known, but they apply it without any justification. And now our task is to show that indeed for this scheme we can imply some kind of Taylor just inserts and write carefully Taylor's expansion for Pn around phi. And question, what kind of difficulty we face on this way? First, we have two natural questions. If we split the integral into the two regions, unknown yet, like this. Then the second integral behaves like approximately like integral of x squared Pn of x dx. And one needs to estimate this for sufficiently small value of Tn. We cannot take it to be big, because otherwise we cannot say anything essential about closeness of Pn to phi. So it should be used for as small as possible, for Tn as small as possible. And then choosing appropriate value of Tn, we should obtain something like O little of n log of n. And this, and we hope to apply Taylor's expansion for the function u log u, and using approximation of phi by Pn's by Taylor, and then this integral is approximately one half Pn minus phi squared divided by phi dx. So although Pn is close to 5, here we have very big factor which grows like e to the power x squared over 2, 105, extremely big on large intervals. So this interval cannot be big. So as a result, we have to balance two problems. To choose Tn small so that to control this integral, but not big so that still to obtain this. And it turns out that to satisfy both requirements, we have almost no window for Tn. And in case where s is equal to 4, this, like in theorem 1, the Tn has to be chosen of the form square root of log of n. So it's not just proportional to square root of log of n. It's very rough.
I mean, the 2 is essential.
Huh?
2 is essential, in other words.
To what?
2 is essential, in other words.
Who's essential?
What do you mean by 2?
There's 2 things written there.
You mean this constant?
Yes.
In general, it should be s minus 2.
But it's essential, that's the point.
2 only for the case 4,
Yeah.
but not for arbitrary s. So it should depend on s. And second is 4 log n. Also, almost no choice for the second term. And then we should add a slowly increasing sequence rho n, and it tends to infinity, but sufficiently slow. Here s.
So even the 4 is essential, in other words.
There is no choice.
In a two-ply Taylor. And then, good, but it's not finished, because let us imagine we are able to estimate, we say that Pn is close to phi, and it's almost, the differences should be like 1 square root of n. Will it be enough? Of course not. If we take here 1 over square root of n, square it, we'll obtain the desired 1 over n, but there is 1 over phi. So we have here square root of 2 pi. Once more, Pn of x minus phi of x squared e to the power x squared over 2. And because it's very big, if Tn is chosen like this factor will create another term n. So it's not enough. And so it's not enough to use theorem like the following. Local limit theorem. Like this. Actually, using the moment assumption, here one can put an additional term like 1 over x raised to the power 4 because of the presence of the fourth moment, which is essential. But nevertheless, if we insert such approximation here, nothing will work. And fortunately, there are sharpenings of such expansions, so-called Edgeworth type approximations. I will write down the definition only in case of the expansion up to the order 3. Introduce another function phi 3 of x, which is standard normal density plus alpha x cubed minus 3x by 6, and here square root of n, 5x. The next approximation will contain 1 over n. While this asymptotic statement is not good enough, there is the following theorem studied by many authors. Including Petrov, Tatalavicius, Bhattacharya, etc. in 60s. So the point is that we reached our term, the error of order 1 over n. Therefore, it's much more effective to insert here instead of phi, instead of this approximation, to insert here the function phi 3 at the expense of this constant of order 1 over n, and then everything will work. And because this term still contains phi of x, it will be squared and will kill this exponential function. So that's how the main idea work. And probably I would stop on this.
Any questions?
Can you actually get convergence and information this way or not?
No, it's Fisher, you mean?
Well, say, yeah.
Fisher is much more delicate. So, and also we will have to reduce ourselves to rather narrow class of densities, for which the derivative is absolutely continuous. Fisher information exists only then. Do you agree with this?
Yes.
For example, you cannot apply.
I think if you convolve a few times.
You cannot apply Fisher information to uniform distribution on the interval. No Fisher information.
Yeah, if you convolve
But
a few
here we
times,
have-
if you add a few copies, I think you'll get that information.
If you add what
Add a few copies.
of the same random variable,
Yeah.
it will be finite
Yeah, sure.
for any.
No, not for any.
No, of course, after convolution properties are improved, but
I think 3 convolutions will always do something like a hat function. Will always give you a.
I forgot here to mention that alpha is equal to a third moment.
Any other questions? For instance, just in the theorem there is on the board, is there a quantitative versions? I mean,
For what?
for instance, just this one, the one you use there, it's just little o.
One can prove the following. Assume that we have a sum of independent random variables, not necessarily identically distributed. And for normalization, assume that variance is 1. Then Dievzen can be bounded by force-Lyapunov ratio or coefficients, which is defined as the sum of force moments. So that in the ID case, we obtain exactly 1 over n. And constant C here depends on D, on the maximal entropic distance for x case to normality. So if you know in advance that all xk have finite d, have a uniformly bounded d, then d of the n will be like this. It's like various n statements for entropic distance. Did you mean this?
I guess so.
He didn't, but the answer, he liked the answer.
Other questions? The same question? No, thank you again.